If you're just joining us, thank you very much for joining us today for our webinar, Important Considerations to Consider When Designing a Custom Spring. I'd like to thank our sponsors today. We're thanking Helical Products Company, who's actually going to be presenting today. And before we begin, we'd like to invite you to check out this webinar before or afterwards and on www.designworldonline.com. We'll also be emailing out the archive link as well. There will be a Q&A at the end of the presentation, so please feel free to submit any questions you have. And if you are on social media, feel free to use the hashtag DWWebinar if you'd like to talk about this webinar on Twitter. I'm your moderator today. I'm Mary Gannon, Senior Editor for Design World, and your presenter is Gary L. Beam from Helical. Gary has been at Helical for nearly 40 years, in which he is focused upon developing closed form involving FEA techniques to understand and predict the behavior of single start and multiple start flexure closures configurated from a helix. He graduated from Cal Poly Pomona with a bachelor's degree in mechanical engineering. And I'm going to let Gary get started here. So we'll turn it over to you, Gary.
Thank you, Mary. Well,
you're welcome.
Good morning, good afternoon, and good evening, folks. I'm Gary Beam, and I'm happy to be here to be able to talk to you about machine springs and wire springs, what the differences are, and what the considerations are that one must use when one selects one or the other. If on the screen you'll see there's a paper that I've written that actually encompasses much of what's going to be presented today, and that will be sent to you in 1 to 2 days following this webinar. Helical Products has been around for a while, and I mention this because that's where I work, of course. The company came to be making beam-style flexures we used in machine springs, but also in couplings. And here are just pictures of some of those things that started this company years ago. So we're going to talk about wire-wound springs and machine springs, and this is really trying to be as objective as possible as looking at the strengths of each. We're going to be comparing cylindrical springs only, and if you look at this picture of wire wound springs, here's some cylindrical wire wound springs, and they look familiar, I'm sure, to everybody. But this is just a fraction of the different types of springs that are available from the wound people. Let me go down a list here, listing some of these things. There are conical springs and barrel springs and constant force springs, wave springs, closed wound springs, garter springs. There's wire forms with hooks and loops and all kinds of variations in there. There's also flat wire forms, and which include negators and spirators, and those are kind of spring motors. So, and this list that I have is not complete. There are many ways that the people making wire product can bend their wire in creative ways to do just what we're trying to accomplish. So, if we look at a machine spring in comparison, you can see it looks about the same, except for the ends are a little different. In fact, these ends are machined because this does not come from wire; it comes from bar stock, and so anything that's really machinable is possible here. So we're going to be talking about springs that are cylindrical at this point only, and a typical cylindrical springs would be compression springs and torsion springs. Here is a picture of 3 springs. The first one's a wire spring. The second one is a single start machine spring. The wire spring is also single started. And the third spring on the right is a double started machine spring. Oddly enough, these springs all have the same rate. The difference here is the material. The two machine springs happen to be aluminum, just for convenience. And the wire spring is made out of music wire. Again, they both have the same rate, but they cannot be compressed the same amount. And as you'd guess, the wire spring can be compressed much more because of geometry availability than the other two machine springs. So one of the first things people look at in springs is the precision of the spring. And I think it'd be good to talk about this a little bit. The wire springs that you buy are about 10% precision springs, and they're available all the time at that rate. And machine springs can be made the same way. When you get the precision down to 1%, the wire springs are going to be a little bit more difficult to make. In fact, you're probably going to have to go sorting through a product line or a production group to find just what you want. And 1% springs are available readily in the machined area. If we look at 0.1% springs, I would doubt very much that you're going to find a wire spring in this area, but I suspect also that they have been asked for it, and they probably can do it, but it takes unusual activities. And we have produced 0.1% springs in machine springs, and we've provided many of those. The point here is just what can be done, but in reality, most springs are in the neighborhood of the 10% range, and so there's no reason to go for precision if it is not necessary. Spring materials for wire folks are music wire, titanium wire, other things, and we see a lot of them, and they're quite successful with that. With machine springs, for one, we don't have the wire product available because it doesn't become large enough in diameter. But also, we tend to use Mar-Aging materials. And 17.4 is a corrosion-resistant steel, as is 15.5, which is very similar to 17.4, but a little bit better melt on it. 455 is a particularly nice product in the sense that it has a 250 KSI yield point. X750 Inconel and all the other Inconels, which have all their high temperature and corrosion properties. There's a high strength steel that we use, a C300, and the 300 comes from the yield strength of that material when aged to 900. There's also a group of aluminums that we use, and both of those aluminums are relatively high strength. The 7068 is not used much, but boy, it's 30-40% stronger than the 7075 D6. The titanium there, the 38644 beta C, is a common item right now in machine springs, and we've had a lot of luck in making those things. At one point, we were the largest consumer of that material in the country just before springs. And then the other non-metallic materials is Delrin, Altum, and there are some others that we can be using. We have to be careful, though, when trying to specify some of these exotic materials, because they may not be readily available, and one may have to wait a while to get them. The titanium has been like that, but even the Inconels and even sometimes the Carpenter Custom 455 will be slow to become available. Talking about sizes, here's a dime, and you can get an idea of what has been made in machine springs However, with wire springs, they get much bigger than this by maybe an order of magnitude or two. And they also can get smaller because as small as the wire can be pulled through a die is the wire size that they can use. So on both sides of the scale, you'll see that wire springs are considerably have a larger range than machine springs, at least at this time. As we look at the differences, here is a listing of attachments that are available on machine springs. Wire springs are pretty limited as far as attachments. So you can see threaded items here, you can see notches, you can see stepped ends, even threaded items on the ends. So all of this, anything that's machinable, well, almost anything that's machinable can be used as an attachment in a machine spring. Now these springs are primarily compression and extension springs. And as we go a step further and look at torsion springs, we have about the same picture, except the nature of the attachments are different. And this is one of the areas that makes particularly the torsion spring attractive. We can, with these attachments, put a pure moment on the end of the spring as opposed to a force at a distance, which becomes a moment. So let's take a look at the coils that are coil information that's available. In section, round is real common for wire. It's unavailable for machined. Square is available for wire, and certainly available for machined. Rectangular, both available. Rectangular with a high ratio, 2 to 1, 5 to 1, 6, 7, 8 sometimes. That's difficult to do in wire, but in a machine spring, that's very common. There's also a longitudinal rectangular, which looks a little bit like flat stock that's wound, and in the wire world, that's exactly what it is, and that's certainly available. But it can also be machined with that, and a high ratio, so having a very wide coil width is available both from wire and from machine springs. The zero width slots, yes, you can close the wire wound springs, and that's available. And with machining, it can be done, but it's a little bit tricky. But we have accomplished that on special occasions. Here's a good one. Zero with pre-stress, something you expect to see in a screen door spring or something like that, and also a lot of other technical things. But this is readily available in wire, and unfortunately is not available in machine spring. So if you need that pre-stressed, the wire is probably the best choice. How about slot widths of, let's say, 100 thousandths? Yep, they're available in both wire and machine. Over a quarter inch, 250 thousandths, it's possible in machine. One will have to look at that, but certainly available easily in the wire products. Number of coils, 1 coil, 20 coils, 50 coils, readily available, except at 50 or 40 or something like this, the machine spring becomes more and more difficult to machine because again, it's coming out of bar stock and has to be kept very stable during the creation of that coil. So there's some concerns there. So there we go. That takes us through what the coils look like and what the coils can be. when people look at compression springs, they often will want to compress them a lot, or as much as they can be compressed. And the wire wound springs can get probably in the neighborhood of 60% of their overall length removed by compression. But that number really drops down to about 40% for a machine spring. In both cases, there's probably a little bit of a gray zone, but as we get to the limit here of around 90 to 100%, of course, neither one can be compressed that much. Here's a typically closed and ground wire spring. Closed meaning that the coils are brought together, and ground meaning that they're as square as they can be made on the end. And this is pretty interesting because this is a compression spring, and the stresses in a compression spring are torsional shear. And the stresses, the torsional shear in these springs goes all the way out to the end. And so the entire piece of wire is active to some degree in providing the elasticity that's desired for the spring. Now, when we look at a machine spring, things are a little different. The torsional shear in this spring ends right about where you see with the arrow, and everything from there on up in this case is a structural member that is going along for the ride effectively, as far as the elasticity is concerned. So this is one of the reasons why you'll find that machine springs have to be longer for the same given performance of that you see in a wire spring. So that also means that if you've got a wire spring that's used in compression and you'd like to have a machine spring to do the same thing, then there's going to have to be some changes. We may have to change the OD or the ID or the length to be able to accomplish the same performance level. So some of the questions are always asked of, what is this thing going to cost? And in all fairness, the wire springs are a magnificent offering as far as good technology at a very low cost, and that needs to be understood. Machine springs, however, are subject to how much time it takes to machine away all the metal. And so the cost of a machine spring can be considerably more. 10 times maybe not enough. But to support this higher cost, one needs to look at what other, why does the machine spring, or why could it be of value? And the integrated attachments is certainly one. The enhanced performance, we'll talk about that due to multiple starts or some other features. We have the potential of having a higher precision than the wire spring, but that depends on the application. And also, with all these additional features, the machine spring should have should be easier to install, and you'll have no sound happening when the coils contact each other, and there will be no debris generated because the gaps always stay open with a machine spring. And as the last sentence says, if you can't find a reason to justify the machine spring, then the wire spring would certainly be the choice that you might have. Just a side point here, machine springs with all their features make themselves easy to deal with. They can go into an assembly easily and come out of an assembly easily, and that's important. Those of you who've worked on cars and done things like brake jobs, you'll know that the hardest part of that job is getting the springs on and off, because the springs just don't have friendly handles on them. But they also make the assembly much less expensive. So there's a trade-off. Metal improvements on wire springs is often significant. It's not uncommon to shot peen wire springs. This helps the fatigue resistance of the spring, and the reason this can be done is the wire springs historically have wider gaps, and so if the application needs shot peening, usually the wire springs will meet that criteria. However, machine springs usually have smaller gaps, and it's hard to get the shot in between those thin gaps, although there are sometimes people still want it. Shot peening really benefits the wire products much more than the machine springs. Well, what we can do, though, with machine springs is we can select high-strength, fatigue-resistant materials that can also provide a significant benefit. Plating of springs. It's not uncommon for wire springs to be plated with zinc, nickel, maybe even copper too. And that's good. Machine springs can be plated, but there's some problems. If you remember looking back at those pictures of them, on the coils there are sharp edges. And plating of anything that has sharp edges on it has a problem right at the edge, because there can be a small electric charge there, and the plating process just doesn't function well. So while machine springs do get plated, sometimes coating them is better with a process similar to painting, but maybe electrostatically applied. So both spring types can be coated in some way or plated in some way, but usually it's different. Aluminum springs, which are a more cost-effective form of the machine spring, are typically anodized, and that anodizing works fine. As we look at compression springs or extension springs, we know that the spring rotates as you deflect it. And sometimes you don't want the spring to rotate. So there are a couple ways of handling this. And one of the techniques that can be done with both machined and wire wound springs is having a right and a left hand flexure on the same part. And the part that you see on its side is just that. And also the little part on its right is just that. They both have right and left hand flexures in them. Now these flexures could be wire wound flexures, but you would not get the attachments that are available. So both wire and machine springs can be made to provide no rotation. And I should say also what happens here is in the middle, where the flexures are just apart from each other, that's where you actually get the motion, but the ends do not. There's also a problem with wire in this sense that you may end up having some moments in the center part may be buckling out a little bit when compressed. The third spring there, the one on its end, has an interesting path to it. It's an inner and an outer spring. The inner spring is a left-hand flexure, and the outer spring is a right-hand flexure, and they're designed to give the same torsional reaction when compressed. And you can see threaded attachments in the ends, and these things, when put together, act with no moment at all when they're compressed or extended. Now, I suspect as you go to the limits of extension, that will maybe become invalid, but you may also have a broken spring at those limits. Okay. What that last spring had, which you may have spotted, is that it was not a single started spring. It was a double started spring. And so here's kind of what they look like if you cut away part of the flexure. You can see the single start there in black, and that's typical. Our coupling lines are made primarily of single started, although we do have some double started couplings. And we also provide triple starts, and so that's readily available. Are there more than 3 starts available? Certainly. And we've made up to 5 start springs. And we find that when the number of starts goes up, the ratio of the elasticities, whether it be bending or translation or compression, take a little bit different path in relationship to the number of coils and thickness of coils and so on. So it allows us to bring a spring into exactly what is necessary by the customer as far as elastic forms. So if we go to the next slide, we'll see what's happening or what the benefits are with this multiple start. On the left, there's a single started spring, which is all wire form. And you can see you're putting a force out on the spring section, but the line of action is through the center line. And so you've got a force at a distance. The force is the big guy. He's what's making the spring deflect the most. However, there is a moment there, and that moment has to be handled in some way, or otherwise you'll have free body motion. And free body motion in this case is something flying across the room. So helical single started flexures have the same issue as all wire wound flexures, which are single started. There are no multiple started wire wound flexures. And if you can figure out how to do that, you probably should hang up right now and start a business, because there'd be a lot of business for you. A multiple started flexure, as you can see in the right, is the helical typical 2-started flexure. And the forces, again, are at the same spot on the coils, but there's 2 coils, and they're opposed from each other 180 degrees. And the moments that's created, the moments are still there, but the moments are equal and opposite, and they net out to 0. So this spring tends not to bend at all. It tends to have just straight line motion. And I want you to remember what we just said, because we're going to show you a picture in a few minutes here, and you'll see why this can become really something of importance to you. Okay, this is Helical's current website, and on that website you can see YouTube's explaining a lot of the details of machine springs, and some of that applies to wire springs. And you're always welcome to log on here and look through the catalog. There's a new member coming to this. I'm looking for the address on this thing. This is Helical. What is the website name? I have help. Heli-cal.com. And this will get you to this website. However, in a short period of time here, we've got a new website coming up, and it's called machinesprings.com. No space between machine and springs. Okay. The next slide we're going to skip because we've already seen the pictures before, so we'll leave a little bit of extra room here for some questions at the end. And we're going to talk about torsion springs for just a moment. We talked about attachments for compression springs, but in torsion springs, the limitations for wire spring is pretty high. They do have a tang. It's a radial tang. It's internal, external, and they're available. They're also available in machine springs, but two tangs are not available, and it takes two tangs to get the perfect pure moment in there without having to force. Now, you can do some things by putting a moment across that tang, but still you then end up having to have everything go through a very sharp corner, and that usually becomes the weakest link in the wire spring. In the machine spring, you can have all those. You can have these tangs, and they can be just machined items, and they have to stand on their own as far as strength is concerned. If there's an axial tang, which is also available from wire, in fact, I worked with one just today. They're readily available in the machine form also. But the dual tangs are not available, whether it be axial, or if there be pinholes or any kind of geometric shapes, are not available in wire and are available with the machine spring. So this is a strong reason why machine springs, if you can handle the extra cost of the machine spring, this is a good use of them because of just the attachments associated with the spring and the ability to have pure moments. Okay. Here's an interesting picture. It's a mass and a spring and a ground surface. And those of you who've been through mechanical engineering or some other engineering areas, and this is a typical single degree of freedom system. Supposedly the motion will be just simple up and down. The problem is that spring that is drawn in these books way back, hundreds of years, that spring doesn't exist. If you put a single started spring in here, you will get anything but single degree of freedom motion. The thing will rock back and forth, and you'll have guides, you'll have rubbing surfaces, and it becomes a problem for any single degree of freedom spring or single start spring. But in a double start spring, remember the moments are resolved, and this thing will literally move up and down with very little lateral activity. And this has become the standard. This double start and the triple start springs have become the standard of dynamic systems, because the spring motion can be just a single degree of freedom, and it can be nice and clean. And so this is a strong reason to use multiple started machine springs. Well, we're getting close to the end here, and these are some machine springs that we've made over the years, and you can get an idea of what they look like, plus the few fly specs in the middle. you see attachments, you see some specialty features. Some of these things come off satellites, some of them come off industrial machines, some of them are medical. So it's quite a consortium, and I'm sure if the wire folks were to have this same slide next to us, it would be about 10 times this as far as all the different shapes that they do. But these are some of the things that are available for machine springs, if that makes sense for you. Again, our website is now written above here, and the news website, Machine Spring, will be machinesprings.com, and a place to look in there is for our list of our factory-trained representatives. So we do have representatives around the world that are probably local to you, and they can come in and help you and act as your proxy in talking to Helical. And while you're certainly welcome to talk to us too, but they can get things going for you. Okay. When we go back to the white paper, you might go through there and you'll find that each of these topics that have been discussed today are in there. Some of these slides came directly from there, or at least some of the pictures came directly from that white paper. And each of these topics will be discussed in a lot more detail. So if you have questions, you can look at that, which will be coming your way in 1 or 2 days. And you can also look at, I think you're going to get a copy of this presentation. You can look there too, and you can also contact Helical for questions and more information. So Mary, I think we've come to the end, and if you can step in and see if there's any questions, let's go for it.
Great, thank you so much. Yes, we do have a couple questions in here. One of them I think is referring to one of your earlier slides. The question comes in, what is meant by precision, 10%, 1%, etc.?
Good question. Precision. This would be the tolerance available for the elasticity. In other words, if you want the part to have a Newton force on it or a pound force on it, how far is it going to deflect? And the percentage would be within that precision. And that's basically and it can be talked about as the actual force. It can be talked about in the deflection, or it can be talked about as far as the rate is concerned. So that's the precision.
Great, thanks. Another question is a little more technical. As I understand the fundamental equation of Hooke's law for spring forces is capital F equals Kx, how is K determined in the design and or testing of a custom spring?
Well, K is definitely is the spring rate, and springs have a rate that's known in compression. They have a spring rate that's a little bit different in extension. That's because they're helical springs, not made by Helical, but the spring form is a helix. The K can be in a torsional rate, both unwind and wind up. It could be also lateral bending. In other words, putting a pure moment across the end of the spring and have it bend over like a leaning tower of Pisa, a real leaning tower of Pisa. And also lateral displacement. So all these things are Ks, and sometimes just one is involved, and sometimes multiple Ks are involved in the desires of the customers.
Great, thanks. Here's another one. If one is currently using a wire spring in a compression application, can a machine spring be substituted?
Well, I talked about that a little bit, but it's the same. It becomes the same thing. Is that you can store more energy in a wire spring, particularly in compression, and in a machine spring, and it becomes an issue of volume. And machine springs have these zones on the ends that are structural, and there's no availability for energy storage there. So the machine spring has to be bigger, and usually it's in length.
Great. Here's another one that just came in, Gary. Are machine springs better in fatigue or force per volume?
That's a good question. Fatigue of the metals, you have to almost go directly to the material that's involved. Some of the metals that are available for machine springs are about as strong and has as high a fatigue strength as anything on the planet. However, in the improvements of the wire springs, you also get some improvement there by putting the outside surface of the spring in compression. And we know that in this case, most all cracks and so on start in tension. So fatigue life, they're both good. We know that we have an awful lot of wire product running at high fatigue. It carried each of us to work today in our valve trains in our automobiles. And when was the last time you broke a wire wound spring in your valve train in your automobile? It's been a long time. So they're both good. They both have their pluses.
Great. Another question is kind of specific about, can I get your coils added to a part that I manufacture?
That's very nice. We're a machine house. We machine metal, and at the end of the day, that we could make that metal look like a spring. However, there are many people out there who are also in the same business. They just don't make springs. They make metal forms and have the capability of making the blank for the spring. So we have a very good customer who is right now supplying us with a lot of blanks, and it works just out perfectly for them because they're able to use their downtime making other things, making spring blanks, and then they just get charged for the process of putting a spring in their blank.
Great. Well, thank you so much, Gary. I think we have a couple more questions, but they're kind of very application specific, so maybe we can get you to answer those directly to people afterwards.
Okay.
So I think that's pretty much all the questions we have here today. So want to just thank you and for everyone for attending the webinar. And want to let everyone know that you can also contact Gary. His contact information was there on the screen. And once again, this webinar will be available as an archive on our website, designworldonline.com, and we will also be emailing it out to everyone who registered to attend. And once again, if you'd like to share any thoughts about this webinar, you feel free to use the hashtag DWWebinar. And as you can see, you can connect with us on various social media avenues. And you can also discuss this on engineeringexchange.com. Thank you once again for your time, Gary. We appreciate it, and we thank everyone for attending. And a special thanks to Helical. Thank you so much, and have a good day.
Thank you.
Thank you. Bye-bye.